Good afternoon, everyone. I hope you can hear me well. So let's pick up and continue from where we left off on Monday. For that, for today's session, what I've planned is a focus on more the algorithmic development and implementation side, giving you a brief overview on how quantum computing programming languages work, how the software stack looks like, and in particular, we will be focusing on a couple of software tools, particularly tailored for neutral atoms type quantum computer. For today's session, we will be mostly focusing on high-level interaction with these devices. So no actual programming experience is required for this initiation session. As you might have seen from the installation guidelines for this course, we will be using a tool called Pulsar Studio. Let me just put the address in the chat. So it's an open access tool and graphics user interface on which we will be relying for the second half of the discussion to do some exercises together and to discover the different ways to program and to implement on particularly a neutral atoms type quantum computer. In order to get started, let's discuss a little bit on how programming, how software development works when quantum computers are involved. For this side, first of all, I prepared a high-level overview on how the different software layers are united when you are working in various different programming environments with potentially various different backends, so various different hardwares, be it quantum computers or quantum emulators using classical computational resources. So let's start on the top. What you can see is the algorithm, the set of instructions that you actually want to implement. So typically as an end user or as a developer, this is your starting point when you sit down and start developing. For this, the first layer of abstraction that happens is defining the set of instructions for a quantum computer based on an available library. So typically we are talking about Python-based libraries. I'm going to show you quite a few of these examples in the beginning to give you an overview of what kind of softwares there are. But the abstraction starts with actually writing your script, your program in a conventional library. Then this library is tasked into translating this code. So this is what we typically call in software development a compiler. So it translates your written code, your legible code into a machine code. So this first yellow layer with the compiler is tasked into translating it to something hardware specific, machine code that is not accessible for end users typically because it consists in a very, very low level manipulations. So it is the task of hardware developers or typically cloud providers to have a complete understanding and full control of this layer because your program, your software is translated into a set of instructions that can then be passed to the actual quantum computer or quantum device. As it's mentioned here, it's not only the compilation is not only just to translate it to machine code. It can also involve further layers. So the QEM is quantum error mitigation. So error mitigation techniques are involved at this level of abstraction in order to try to anticipate and reduce potential sources of errors based on the code you have written on your site. On top of that, we software stacks will be adding the QEC, so quantum error correction layer at this phase as well. So as you might know, quantum error correction code is a low-level middleware section, so a software layer that is added on top of the physical architecture of a system to ensure that you can either create logical qubits out of physical qubits or using different paradigms in order to drastically reduce error rates. So this is something that's still in development for most software stacks. This is more of a schematic overview of where this would be situated. So once this compiler has defined the machine code itself, it then gets passed on to the respective backend by means of what we call pulses. So these pulses can be laser impulses, these pulses can be electric impulses, it can be electromagnetical signals, depending on the different type of hardware you are using. They get translated into specific physically parameterized instructions for the actual enabling hardware and for the actual components of the technology. Or alternatively, if you are executing your code, it is at this point that it will be passed over for more conventional simulator or what we call an emulator. So emulators are nothing else but CPU or GPU racks typically that have been set up and parameterized to behave like a quantum computer. So this is on the right-hand side of the section. As you can see, developing your code doesn't really distinguish from an emulator-based or a physical QPU-based execution up until this very, very low-level pulse definition layer. So technically, the same code you are developing and testing on your own device with a local emulator or on a remote emulator via cloud access can then be used the same way to be passed on to the actual physical quantum computational device. This makes a lot of the computation, most of the software development paradigms much easier because you have easier access to test, to optimize your code before having to rely on the actual physical QPU. But once you need to rely on the physical QPU, it is there that it's actually distinguished. So these pulses that have been defined then are passed down to specific physical instructions that are dependent on the actual hardware. So as you can see, for electron-based qubits, so superconducting devices, quantum dots, spin qubits, and such. These are getting translated into microwave pulses, so mostly electric signals, in order to be able to interact with the superconducting microchips in the machine. For trapped ion and neutral atom systems, these are typically translated into actual optical laser pulses and parameterizations of the different optical and magnetic setups. And for photonic qubits, they are controlling the various aspects of the machine depending on what kind of photonic device is used in the backend. So this is how typical software interaction works. Of course, you as a developer would only see the surface of this, so the quantum source code layer. I just wanted to illustrate that on the back, there are multiple layers with multiple different levels of abstraction and translation layers that are happening, which can make certain implementations less adequate or even infeasible, depending on the backend you would choose. I wanted to illustrate a little bit more particular way of going about software development when you are using an analog type quantum computer. So as you may recall from Monday, an analog quantum computer does not have quantum logic gates. It's not operating on a circuit level. Instead, it is tasked by interacting with the quantum bits on a continuous in time level with typically a single pulse, so a single but continuous in time energy transmission. This makes it particularly adapted for certain types of tasks, but it also makes certain elements of the quantum computational stack from a software level different or much simpler. So as you can see here, you can still find a similar layer of abstractions given your actual use case, your algorithm you want to implement. You define the formulation of the problem. This can be the actual source code, or in certain cases, it can be made one layer of abstraction higher already using different primitives, which then gets converted into, again, machine code, either directly, so this refers to the graph embedding type interactions, or indirectly using quadratic unconstrained binary optimization type solver or Ising model or company. We will see a couple of examples of this. It is at this stage, so this very, very low level, then it gets translated into physical qubit specific instructions, be it on an emulator-based execution once again, or execution on physical devices. As you can see here, for analog interactions, there are mainly two types of physical backends that are distinguished: superconducting type qubits. If you have used D-Waves quantum annealer, this would fall into this category, or neutral atoms type systems, which are natively an analog system. So the layers of abstraction are still similar. However, the translation process can be made much more efficient, and the entry point for the users can be much higher because the focal point of the machine is a bit more specific than it would be for a generic quantum algorithm. With that said, I wanted to give you a brief overview of the currently available software libraries. So as you can see, there are quite a few of them. So here I'm mentioning software stacks available from different cloud providers or a couple of the main hardware providers representing different technologies in order to illustrate the diversity of the field. So there is really not a single uniform quantum computing language out there. That is not the case for classical programming either. As you might know, we have a lot of different programming languages out there that have different uses. But with quantum computing, it is even worse, the scenario, in a sense, because the available tools are still very, very much hardware dependent, because a lot of the interaction is happening very, very close to the physical machine. Even the highest level of abstraction for current quantum computing software could be considered as an equivalent to assembler level interactions on a classical computer, which is still a very, very low level interaction, and people typically don't deal anymore within classical computing. Nevertheless, we are going to discuss a little bit in detail two software tools in particular. So I wanted to first and foremost showcase some of IBM's tools, so mainly the Quantum Composer and Qiskit, being that it is one of the currently existing main software development environments, even though it is still a system that's mainly focusing on superconducting type qubits. That's how most of its backend is set up. So most of its emulators, so it's particularly adapted for that kind of technology. But as you can see here, depending on a different technology, they can support different types of devices, and they can allow for different levels of abstraction. So on the left, I've distinguished going from a visual graphics user interface type experience. We are going to see two today, and then it goes down from a higher level thematic libraries, or maybe even oriented to machine learning type interactions, a low level machine language or close to machine language, and it also mentions what type of systems it is actually supporting. So in the first section, the first four columns are actual hardware providers, and as you can see, the tool they have developed is very much specific to their type of hardware. Contrary to that, Microsoft, AWS, and Evidence software tools are much more all-encompassing. So they are taking into consideration different types of technologies in order to accommodate actually the different devices that they are supporting. And one of our focus points for today is going to be to give an overview of what Pasqal is currently have available as software toolsets. A good thing with these software tools is that most of them are open source, so anyone can just get access to it, download it, play it around with it, typically with local resources, so executing the code on your own device with a local emulator backend. In certain cases, companies or service providers can provide access to cloud-based computational resources, either emulators or in some specific cases, even to the physical machine, free of charge. With that said, let's first take a look at Qiskit. So Qiskit is an open source Python library. This was one of the first quantum computing programming language in a sense that has been developed, being that IBM was one of the first main players to appear in the field with this superconducting technology. So it is currently widely used for educational purposes and for algorithmic research in various research labs. It is partially due to the fact that since it's being one of the first tools to arrive, it has had time to develop its own community. Moreover, it has a very, very good documentation that has been catered for the past 7 or 8 years now that I wanted to briefly illustrate. From IBM's website, you have a specific Qiskit page that helps you really get started. They have made major revisions since the Qiskit software stack has reached the version 1.0, which happened almost 2 years ago now. And they have extensive amounts of tutorials, guided notebooks for their various parts of the software. And they also provide or also organize quite a few hackathons to get more people involved. Actually, the Qiskit software stack has multiple different layers. So a couple of years ago, they made the single Qiskit software stack divide into specific thematic ones. So currently we have 4 high-level Qiskit derivative software stacks that are catered for specific types of applications and specific fields, and therefore support compatibilities with the currently existing Python libraries within that field. Other than that, the core capabilities have been still reunited, and catered for in what we call Qiskit-Terra, which is the main Qiskit interface that everyone would be using, supported by various backends, which are typically superconducting-based emulators, be it locally or on the cloud. One more thing I wanted to showcase, because it's interesting to know about at the very least, is what we call the IBM's Quantum Composer. Some of you might have already seen this tool. So it's really an interactive graphics user interface that allows you to design quantum circuits. And then using the feature, you can really construct various setup scenarios and test up to a certain number of physical qubits, how it would behave if you were to execute it on the actual device. So the platform really looks like this. It's a very, very simplified version of it that supports a no-code environment in a sense. So you can really get by just using the tool set on the left. So the different icons refer to different quantum logic gates or different actions you can make on a digital quantum computer, or in some cases specifically on a superconducting type device. The main part is this central section that allows you to place, for instance, these logic gates, and then on the back end, using your emulator, your browser's resources, it's simulating how it would behave. As you can see on the lower part, I directly get a feed if I were to put Adamard type quantum logic gates on my 2-qubit system. It has created a 4-way entanglement, which is being illustrated by probabilities, and it also gives a quantum sphere-based representation that you can switch around if you prepare a state vector-based visualization. What's more is that behind the scenes, it is actually generating code for you. So you can see here the corresponding open chasm code, but you can also switch for the corresponding Qiskit code. So you do not need to know any kind of Python programming to get started, build a quantum circuit to play around on the visual interface, and then you can recover the corresponding code, the corresponding Python code that you can just insert into your Python script, into your notebook, your Jupyter notebook, and then further fine-tune as well. So I just wanted to showcase this tool because I think it's very, very interesting, especially for a quantum logic gate-based setup. So developing and getting a better understanding of quantum circuits. And Qiskit has a very, very good tutorial. So for that purpose, it can be very interesting to dive deeper into that. However, for today's session, this is not the main objective. Our main objective is to learn much more about neutral atoms type systems and to get a first hands-on experience with software stacks tailored for the particularities of a neutral atom system. For this, I wanted to remind a little bit how a neutral atoms-based quantum computer works. So if you remember from Monday, this is probably the time to make a tea for yourself. If not, I wanted to go through once again the main steps in operating a neutral atoms-based quantum computer, because this will be essential in getting a better understanding of how our laser pulse-based and atomic system-based software stack is operating. So neutral atoms type system is an optical installation that uses various lasers to trap and then manipulate individual atoms. So everything is being manipulated by lasers. Therefore, on a machine code level, a very low level, you are required to parameterize these different optical setups and lasers in particular. So the low-level coding environment will eventually ask for you to define some parameters of the lasers or derivatives of these parameters that correspond to physically engineered setups for the laser system. As a reminder, so in the neutral atom system, you are given a choice of atom as a base of your computation. So in Pascal's case, we are using rubidium atoms, but this is not the only viable choice. And once you are given this atom, you have two main components for the computational cycle. The first is to create the quantum register. So this is the set of atoms that you need to start your computation, provided in a specific layout. So herein lies the first particularity that software stacks need to support, is the fact that a neutral atom system does not have a fixed architecture. It can have, but that limits severely its capabilities. Typically, it allows for the user to define where they want to have their atoms, so their physical quantum bits. Therefore, the software stack needs to be able to handle this flexibility on a very, very low level at the very least. So in our case, we are defining the positions for the optical tweezers to trap the atoms. Typically, this is done on a vertical plane, so in a two-dimensional layout. Again, you can see a couple of examples with the lighted dots being individual atoms trapped at specific positions, illustrating different configurations. And once this layout is established, then comes the second step of the interaction, which is based on another set of lasers to send energy, to send information to this quantum system to make it evolve. And it is through this evolution that we are actually carrying out the computation. In between and at the end, there are different readouts that are being made by fluorescent imaging. That's how we obtain these images. But from a programming perspective, this part is really handled on the machine code level. So as an end user, you won't be needing to worry about that. So to recap, for the neutral atom system, everything is based on different sets of lasers that needs to be set up to define two key ingredients. The positions of the optical traps in order to trap the atoms. So to have your physical qubits in a specific arrangement, in an arrangement that's suitable for your algorithmic implementation. And then parameterize lasers that will send the information to make the system evolve according to the algorithm you want to implement. As a revision, the actual what's happening inside the machine, again, most of it is something that you as a user won't be needing to worry about because it's handled on the machine code layer. So trapping the atoms comes first, creating enough traps to ensure that the machine is able to catch a sufficient number of atoms, then repositioning the atoms in the computational area. So this is the section that the user will need to define where they want to have atoms. It is then up to the machine to propose and set up additional traps to ensure that it is able to catch enough atoms for the computation. It is then up to the machine itself to reposition the atoms in the specific position. And so everything before that is the pre-processing phase that's handled by the machine. The entry point for the user will be the positions in which they want to have atoms and the quantum processing. So this last segment in which a user-defined sequence of laser pulses is sent to this computational register to excite the system to instill different dynamics to carry out the actual computation. After which the user, as a feedback, receives information which is not an image-based information, and the user actually gets as a feed zeros and ones, or with consecutive executions, probability distributions on the various quantum states and that can be attained by the system. So how it looks like in actuality, let me restart it. Hopefully, yeah, it's working. Perfect. So what we are going to look a little bit more into detail today is the Pulsar Studio environment that features in a graphics user interface type setup with a practically no-code environment, the aforementioned steps. So we are going to go through step by step how you would go about defining your very first quantum script or quantum code by using this interface. Again, the two main features or the two main components that you as a user need to worry about when you go about the actual implementation phase is first defining the quantum register. So on the top left part is what you can see is the placement of the atoms. Each highlighted dot with an annotated Q index is an individual atom's position. It is there that you want to have your atom for the computation. And on the lower section, what you have is the time evolution of the laser pulse of the sequence of informations you want to send to this quantum register to make it evolve. And on the top right part of the screen, what you can see is the evolution of the quantum state. Since we are working with emulators with this toolkit, so everything is run on your web browser, you will see that you have access to intermediate states. This is not the case when you are executing on the physical device because you cannot just stop in between the computation to get access to intermediate quantum information. With that said, I wanted to first give you a brief overview of neutral atoms based softwares that are out there. All of these toolkits are open source and provide various entry points depending on your level of maturity in Python-based programming or quantum programming in particular. So illustrating with a slightly different experience and our main tool for today is going to be Pulsar Studio. And this has been developed as an extension for Pulsar, which is our main software stack, our low-level Python library that serves to interact with any kind of neutral atom system. So it is really tailored for neutral atoms-based systems, but it supports both analog and digital quantum computational paradigms, as we will see shortly. So this is really a graphics user interface, so visual environment that allows you to learn to experiment similarly to IBM's Quantum Composer in a no-code environment. And similarly to that toolkit, it also generates the code itself for further repurposing, but we will look into that later. On top of that, currently from Pasqal side, we have two software libraries available. And the first one is Pulsar, which, as I mentioned, is our low-level, so machine code level Python library, an open source toolkit that has been developed initially to serve as direct interaction with our quantum computer. Nowadays, it is still the main entry point and the main language of interaction for our quantum computers or our emulators. So it is compatible with quite a few Python libraries for low-level algorithmic development and implementation. And it is also the main tool that you would use to access remotely different tools, different computational resources, be it cloud-based emulators or the actual physical device. As I mentioned, on top of that, there was Pulsar Studio that was built to serve as a graphics user interface for this actual language. And last year, we have released a second Python-based software stack, which is called Cadence. It is also an open source Python-based library. However, it is a much higher level library in a sense that it is functionally and architecturally equivalent to IBM's Qiskit. So it provides access to primitives. It features both analog and digital, as well as digital analog type quantum computing. So you can implement quantum circuits with it. You can implement a fully analog code. You can do a mixture of both, bearing in mind that most of the digital-based, so quantum logic gate-based code can only be executed on emulators, because the current first generation physical device of Pasqal only supports an analog way of interacting. However, on the emulators, you can already develop and explore and experiment with both digital and analog type interactions. And there is also compatibility with a lot of the currently existing machine learning toolsets. So Cadence is really viewed as potential entry point for future end users, tailored for not only the next generation hardware itself, but it also is tailored for more high-level interaction and compatibility with various open source software stacks and libraries relying on either operations research or artificial intelligence type explorations. We will go a little bit more into detail in these two software stacks in next week's more advanced sessions. So both these software tools will be featured during our respective courses, with Pulsar being featured more for the optimization side, and Cadence will be our main tool of exploration for quantum machine learning based exploration that's coming next week. For now, I just wanted to showcase that these two open source libraries are already available for everyone to download, to get set up, to start exploring. They come with their own local emulators, so all the code you would develop can be locally executed up to a certain number of physical qubits, which of course depends on your own computer's metrics and characteristics, because trying to execute code on a higher level of physical qubits for an emulator is not only very taxing for the RAM and the memory, but for the CPU activity as well, depending on what kind of emulator you're using. So let me briefly stop here for now to look at the chat if there are any questions. I know some of the initial sections were a reminder from Monday, but I talked a lot about the different software development and tools. So I don't see any questions for now, so I think I can continue for the next part, which is going to be much more interactive after a quick introduction to lay out the foundations. So if you have access or have created access to Pulsar Studio, I will invite you to work alongside me to explore a couple of examples within the toolkit. In order to get started, I want to remind and re-precise a couple of notions on which we will be relying on in order to start our very high-level exploration to create, in a sense, our first neutral atoms-based quantum scripts. The first notion that I want to allude to is that there is an inherent connection between graphs, so what we mathematically refer to as graphs, a collection of nodes with edges, connections being established between certain nodes that arise in various mathematical setups or as part of certain algorithms. These graphs, mathematically speaking, can be connected to neutral atom systems quantum register. So what we call a quantum register is the computational area wherein we want to perform computations with our atoms. So this is in the heart of an intra-atom system where you are trapping the atoms and then we'll make them interact with each other. The correspondence is done as follows. We can identify each atom trapped in the quantum register as a node. So visually can be represented as a node. It's not hard to envision because it's already a highlighted dot obtained from the fluorescent imaging. The trickier part that's not actually visible from the feed, from the camera feed we get, is how you define edges, how you define connection between these atoms, between these nodes. It is actually based on the physical interactivity in between atoms. So if you recall, we will go into it a little bit further into detail, but we are using atoms that are capable of Rydberg type hyperexcitation, meaning that we are able to send the outer electron layer to a very, very high orbital, so very, very far from the atomic kernel. This allows us to entangle atoms that are not necessarily super close to each other. But is represented by edges in the graph setup, and it is visualized with these extra dotted lines, which have been added on top of the image that we obtained to illustrate how we can formulate a graph from an atomic register. Is a distance-based interaction, illustrating that if two atoms are sufficiently close to each other, so physically sufficiently close to each other, they can enter into interaction by means of the Rydberg blockade if they receive enough energy. So the edge itself represents a physical interaction, which is van der Waals type dipole-dipole interaction, or in the capability to interact with each other. This is distance-based in a sense that there is a cutoff point. There is a limit on the distance after which two atoms can no longer enter into interaction. Therefore, the graph it gives rise to is a specific type of graph that we call a unit disk graph. So this is a specific mathematical construct in which each node is associated to a coordinate and edges are drawn wherever two nodes are distance-wise sufficiently close to each other. So you can see an example here on the left drawn on the map of France for convenience. And then the translation can be made to an atomic register in which we have drawn the dashed lines, the distances that are sufficiently close for interaction, giving rise to actually a graph structure, which in this case resembles more an actual molecule than anything. But depending on the layout, we will work a little bit with this part. It can have various different effects. So this is the first part, that the geometry, the actual layout of the quantum register can be represented as a graph, which is going to be a key element for upcoming sessions as well. The second element is how the interaction works. So as I mentioned, we are working with atoms that are capable of a Rydberg type hyperexcited state, meaning that we are able to send the outer electron layer, the outer free electron, to a very, very high orbital. So in order to create long-range interactions between atoms. In actuality, this is the base to define the reference points. So here in the middle, you have a schematic representation of the energy states that the rubidium atom in particular can reach. So the base fundamental state on the lower or lowest possible orbital. So on 5s for the single free electron is our ground state, which is our zero reference information. The highest state that we are currently reaching with our laser setup, it can be pushed further, but it depends on the actual needs of the machine, is on the 60th orbital, which is considered one of the hyperexcited states attainable by the rubidium atom. And this constitutes the other reference state, so the one information. Technically, anything in between is fair play in terms of superposition. As we have seen yesterday, this is one of the fundamental principles coming from quantum mechanics, that information can be 0, 1, or superposed, which manifest physically in an intermediate energy level. Why I'm illustrating this is that I wanted to allude to a couple of other orbitals, low orbitals, what we call hyperfine orbitals. So these intermediate low-level states are the main means to create quantum logic gates on a neutral atoms type system, because you can efficiently interact and interchange the atoms in between the 5s, 5p, and 6p orbitals. And you can do this relatively quickly, which is essential to do a quantum circuit, a quantum logic gate-based implementation. Nevertheless, as I mentioned, on the actual physical setup of the current generation device of Pasqal, we are not supporting local interactions, so there are no implementable quantum logic gates on the physical hardware. However, that does not stop us from developing code with quantum logic gates in mind. Here, I just wanted to illustrate that there are two interaction regimes we are working with. The high-end orbitals, so the hyper-excited states for long-range interactions and entanglement. This will be our main means in order to have atoms communicate with each other, in a sense. And the hyperfine, so low-energy states that will serve us to define local interactions in particular. With that said, so let's now look at the actual tool a little bit closer. So I will try to put it in full screen so that it becomes a bit more visible. So when you load up Pulsar Studio, so I provided the link in the chat, feel free to follow along by listening to me. You're welcome with this creating new experiment panel. So I will use this to explain how you would go about starting off your experimentation. So as you can see, there are multiple things that you can get started with. There are two main components for this interface. Again, defining the geometry, defining the physical layout of the quantum bits of the atoms is part of the implementation, and it has a very, very crucial role. So the toolkit by default proposes you a couple of different patterns, a couple of different structured layouts that you can tweak if you want. So if you want a structured grid on a rectangle or a square lattice, you can get started with that. You can ask it to generate the pattern, but you can also switch to a circular arrangement of atoms or even a triangular shape. Once you have made your selection, you can just click on generating the pattern itself, and then it also already creates the corresponding layout. So as I illustrated beforehand, our quantum register, so the placement of the atoms, can be represented by a mathematical graph structure. So Pulsar Studio relies on this representation to provide you with an intuitive visualization. So each node that has been assigned corresponds to one atom. And then you have the visualization of these edges, so the connections in between atoms that illustrate which atoms can enter into an entangled state together. So in this sense, this graph representation is a visual feedback of how closely connected, how well connected your quantum register is, which quantum bits can you entangle to create whatever algorithm you want to do. The additional feature of this platform is that it's really fully interactable. So you can just click on any of the atoms and move them around if you want. So as you can see here, I can really place my atom not anywhere I want, but up until certain limitations. So I can freely move around, and if I want to create an arbitrary layout, I can really go around and fiddle with it to have the geometry I want, which can be as arbitrary as you would want with certain physical limitations. So first of all, as you can see, the edges are dynamically drawn. So if you move two atoms too close, the edge becomes thicker, illustrating a closer, stronger interaction. If you move two atoms too far away from each other, the edge disappears, illustrating that you've reached the Rydberg blockade limit, so the atoms can no longer enter into interaction. Additionally, if you move two atoms too close to each other, you have this visual representation of a circle that appears, and the interface physically forbids you from moving two atoms too close to each other. The reason for this really goes back to how we go about with the traps themselves. So we use a focused laser light to trap the atoms themselves. However, if focus points were too close to each other, the two traps or the atoms in these two traps would start interfering with each other. Therefore, it would potentially pollute the experiment. So two traps are by default, by the machine, are not allowed to be placed too close together. This is something that, from a software developer perspective, can be seen as more of an arbitrary choice. It more matters when you would develop on the physical device. And herein lies one of the main advantages of relying on emulators. So on the right-hand side, you can see different panels. So you can see information on the register itself when you move around the atoms themselves. You can use this panel to define the coordinates. If you don't want to move around with your cursor, you can define the coordinates yourself by hand. The main feature for now that I want to showcase now is the actual device. So Pulsar Studio is entirely running on your web browser. So it has a backend, a local emulator that relies on computational resources accessible for your web browser only. Therefore, it has its natural limitations. It has its limitations naturally, but in a sense that you cannot emulate with Pulsar Studio more than 12 atoms because it would require too much resources, and then that would inhibit the capabilities on certain devices. So it's a safety measure that's implemented. However, nowadays Pulsar Studio is also connected to cloud-based emulation. Therefore, with sufficient cloud access, you can run larger experiments as well. For now, we will focus on the local emulation. And for both emulations, you, from a software developer perspective, have full control on the device you want to run the experiment in. So by default, you have access to two types of machines. So there is a mock device, which is a simplified prototype that supports both analog and digital interactions, as we will see. And you also have access to what we call Fresnel, which is a digital twin of our first generation quantum computer. And it contains all the physical constraints and setups that we have on the physical machine that you can just import and work with it in this visual interface. What I wanted to showcase is the fact that it supports something that will be coming into play with later generations, which is, of course, the dimensionality. As I mentioned, we are working on vertical planes, so two-dimensional planes. It also allows you to set up the Rydberg level, so how far the atoms can reach out. So this is something that you can artificially tweak if you want. It also controls the minimal atomic distance and the maximum radius in which defines your working zone. So these can be artificially modified if you want to play around a little bit with the system. So you are really changing the backend, creating a new virtual device in a sense. If you want to explore with that, for now, we are going to leave it as it is by default. The second part of the experiment, so once you have created an atomic layout that seems suitable for you, would be to create the laser pulse. So define the energy that you would send on to this atomic register. So as you can see in the bottom, for the mock device, you have different channels accessible, and you have some visual illustrations on what they, what type of interaction they are focusing on. So you have what we call local channels. So these are emulator-specific channels that allow you to target individual quantum bits, individual atoms with specific laser pulses. The Raman channel refers to the interaction with the hyperfine state. So if I go back to the presentation, the Raman channel corresponds to these low orbits that we would use to create quantum logic gates. The other that we have, the Rydberg channel, corresponds to the high energy, hyper excited states, both in a local interaction and in a global interaction setup. And then you can define different pulses. So if I were to add laser pulse, suddenly I have visual representation of a laser pulse sequence. I can see its time evolution of both of the 2 degrees of freedom, so both of the parameters that you can change around. And I can also see on the right-hand side, I have an extra panel that has been added that allows me to change all the different parameters for the experiment. So when you are working with neutral atoms device for setting up the laser, you need to account for 2 degrees of freedom that can be represented physically in different scenarios. From a Pasqal perspective, we are working with the amplitude parameter and the detuning parameter, which provides the 2 degrees of freedom for the interaction. However, in terms of the actual time evolution, you have access to many different ways of interacting with the system. So as you can see here on the right-hand side, with the waveform, I can define what type of laser pulse I want to emit to my system. So it can go anything from constant all the way to Gaussian curve or even an interpolated section. So it really allows you to customize as finely, as precisely as you want this interaction, which really illustrates this continuous in time evolution that can be made as complex and as meaningful as possible. Similarly, for the other parameter, the detuning parameter, this allows for different forms as well, and it also allows you to work with the different physical parameters from the actual duration that's measured in the horizontal scale in nanoseconds. So you can see the time, the elapsed time in nanoseconds. So it's a very quick interaction. And you can also change different parts of the shape. Once you think you're satisfied with the interaction itself, then you can execute your code directly in the interface. In order to execute this, execute the code, you just need to click on this right arrow on the top right part of the screen to play. And if you have defined the system with less than or at most 6 atoms, it will automatically execute. And we will see examples when you have no more atoms, it needs to pre-compile and then it can be executed. If I click on it, it was a very, very quick interaction. So a lot of things happened. I will try to stop in between. So as you can see, the whole quantum register is highlighted in purple or violet. This illustrates that we are doing a global interaction. So we are sending the laser light, the same laser light to all the different atoms at the same time. we were working in a global channel. And on the top right part of the screen, I have access to the intermediate quantum states because we are doing an emulation. I can change the display for different setups and values. I propose to stick to the ground Rydberg measurement. So ground state, hyperexcited state to actually get zeros and ones. And through the time evolution, you can follow how the information, how the repartition of the different quantum states has evolved. Additionally, what is supported is that if you hover over a specific quantum state, it actually highlights you on the quantum register, as you can see on the left hand of the screen. It really highlights you which atoms became excited, so which ones are in the one state, illustrated by larger circles, and which atom stayed in the zero state. With this histogrammic representation, you have access to not only the probability, but you get a visual feedback of which were the predominant states that got excited at the end of this execution. Of course, there is no actual meaning behind this sequence. It was just a quick illustration. What I wanted to show is that you can also follow the evolution by actual quantum states. So the experiment can provide you the actual mathematical repartition of the decomposition of the actual quantum state. And you also have access to the code itself. So as I mentioned, this is a no-code environment in a sense that you don't need to know any kind of Python programming to work with the system. The code is being automatically generated. So if I move around an atom, as you can see, the Q1, the atom is being highlighted in the code, and it automatically updates the coordinates that were assigned. Similarly, if I'm working with the pulse, this will in turn highlight which sections of the code correspond to defining the laser pulse for the interaction itself. So the whole experiment is generating automatically the code for you. You can copy paste the code and then work with it locally in your specifically set up Python environment if you want. But if you don't want to look at the code at all, or you're not at ease with programming with it, you can really just look at the quantum states themselves. So I think there are a couple of questions in the chat. So let me go through them quickly now that I've gone through the essentials of Pasqal Studio that can give you some time to get connected if you're not already connected with the tool. So can this kind of interaction change not only Rydberg state, but also ground state? So the way it works is that the atoms that are being trapped, and the experiment always starts on the ground state. So on the ground state, the interaction range of the atom is actually its outer orbital. So you would need to have two atoms physically next to each other for them to enter into interaction. You need the excitation to observe any kind of interaction. And due to the limitations, so this physical barrier, which is the optical trap, which is not a point in space, it's an actual sphere. So the laser focus is not a single point, but a specific small area. The atoms cannot really move too close to each other because otherwise it would destroy the properties of the trap itself. So since atoms cannot physically be close together, you need these hyperexcited, these high energy levels to have the atoms interact with each other outside of the trap. So the atom itself is staying inside the trap, but its interaction range can reach outside of the trap. So it's not full entanglement in a sense, and you can really play around to find the best layout that these edges give you a visual feedback of how many atoms you can fully entangle. So a full entanglement would be a fully connected graph representation you can tweak around the system to allow for much more efficient compositions. In the mock-up device, I think if you're good, you can place 9 to 10 atoms in a fully entangled state at the same time. Otherwise, with the improvement of the traps, so reducing the size limit to move atoms closer, or increasing the interaction range, moving to higher order Rydberg states allows you to create larger entanglement blocks. Nevertheless, since we are dealing with hundreds, even thousands of atoms in the register, it will not be fully entangled. That's a particular feature of trapped ion systems only so far, but it supports many-to-many interactions. So you can really create rather large entangled blocks within the atomic representation. So it's not full entanglement on the whole 100 or 1,000 atom system, but you can have 10, later on 15, 20, 30 atoms in a fully entangled state, which is already quite interesting for various dynamical setups. So how many qubits? So technically there is no limitation, or at least I don't think the system itself limits you to add atoms. So I can just continue adding atoms one by one to create a rather large system. At some point, it will stop me because I will reach the limit of the interaction zone. So if you remember in the device specification, one of the parameters was the maximal radial distance, which defines how far I can place atoms from the origin itself. But for visual representation, you can put, so just working with the register, you can put the 100 atoms in the system easily. However, you won't be able to execute any kind of code on it. So as you can see on the top right part of the screen, it warns you that there is no emulation available for more than 12 atoms. This is this safety reason that for more than 12 atoms, depending on your PC and the allocated resources for your web browser, it might take too much time, or it might even crash the web browser. So this has been implemented as an artificial break for the actual emulation. But just for the visualization, you can technically work with rather large system to check different configurations if you want. So if we set the node structure after moving nodes in this program, is there the same structure of atoms in the real devices? Yes, so the real device features this full flexibility as long as you were working with the corresponding digital twin. So here in the Fresnel machine, to take into consideration the physical parameters of the system. In this case, meaning that how close two atoms can be, and what's on the maximum radial distance. So what's the Rydberg level, the minimum atom distance, and maximum radial distance. If you have respected these constraints, then the machine is able to reproduce that configuration. However, so what you need to keep in mind is that the layout then needs to be fixed for the experiment. So you cannot move the atoms around during the actual computation. If you want to have atoms moving around, then that would imply that you would need to start a new experiment. So it's not dynamic in this sense. The atoms are not moving on the fly. This is something that you need to set up in advance for a specific experiment. You need to define where you want to have the atoms. So you won't be able to move around the atoms. It's not that kind of system. The actual Pulsar Studio, as I mentioned, is running on your web browser. So it's a local emulator or simulator, if you wish. And it also supports cloud-based emulation backend. For now, it is not connected to the actual physical device. However, the code you would develop here could be used to run the same experiment as long as it's compatible with the physical device. It can be used to run the same experiment on the physical device. However, at this stage, there is no visual representation and feedback with the actual physical device, sadly. Yeah, let's see. Frana, yeah. Experiment must reset. I'm not sure why Fresnel is not accessible for you in the devices. It could be related to the account. I will need to check that. For me, it managed to load with no problem. So we can briefly go through the different parameters for the machine. So as you can see, the Rydberg levels are set to 60 instead of 70. The maximum number of atoms is kept as a safe cap of 80, even though you could push it for 100. As you can see, all these parameters are barred out, so I cannot modify it. It's really a digital twin representation. You have a minimum atomic distance of 5 micrometers and a maximum radial distance of 38 micrometers. So if all else fails, you can modify your device to support this. The additional particularity that you need to pay attention to is that the only channel available is the Rydberg global channel. So as I mentioned, in the current setup, we can only do analog interactions. So only the global channel is accessible for that reason. So the 0 state corresponds to the ground state of the atom, and the 1 state corresponds to this Rydberg hyperexcited state that can be set. What's your Rydberg level? So 60th or 70th orbital. So yes, you are correct. The ground state and the Rydberg state are the two reference states. So for the FTQC setup, of course, we are not there yet. None of the providers are there yet. But indeed, so this tool is working with Pulsar. So Pulsar is our machine code level environment that's directly working with the physical qubits. So in an FTQC environment with quantum error mitigation, quantum error correction involved to create logical qubits, you as a user would create potentially the pattern for your logical qubits. And it would be up to the machine to allocate a block of physical qubits to that. So that would be a layer of abstraction above for the system to define. Of course, that's not available in the current system yet. That's still something that's being explored. So the meaning, as if I go, let me just create a quick experiment to illustrate it. So when you define laser pulses, you have access to two main parameters, amplitude and detuning. So we will discuss a little bit more in detail what it means algorithmically, because depending on the type of algorithm you want to use, it can have different meanings. But essentially, when you talk about amplitude, you think of you have to think of your Hamiltonian, your driver Hamiltonian. So this laser pulse acts as an external source of energy for the whole system. The amplitude defines the positive term, so the source term of this interaction, and the detuning defines what we call the sink term, so the negative coefficient term in this interaction. So basically, in your Hamiltonian formulation, in your operator-based representation for the interaction, this is the source term for the one-body interaction. This is the sink term for the one-body interaction. So this is with a positive factor, and this is with a negative factor, in a sense. That's the visual representation for it. Okay, so now that we have explored and discussed a little bit about the tool set, let's move on to some actual experiments. So I'm going to click again to a new one to illustrate another feature. So if you click on the plus icon, it allows you to create a new experiment. So that's what we were playing around for now. But it also allows you to load one of the predefined experiments. So currently there are 3 predefined experiments, predefined examples at your disposal. So we are going to go through them one by one. The first that you could load is the antiferromantic state experiment, which loads tiny rectangular grid, so 6 atoms and 3 consecutive pulse sequences of relatively simplified shape. So let's execute this example and see what happens exactly. Oh, let me check. I think something's broken here. It was working beforehand. Okay, interesting. No, I'm losing something there. Let's reload the experiment. Oh, it's being unruly. Never mind. We will see it on another experiment. So it's not a huge problem. So this, as the name implies, the antiferromantic state experiment refers to a specific setup in which you are placing atoms, simulating electron spins in a rectangular grid. And then you excite the whole system in an adiabatic evolution way in order to define what we call an Ising Hamiltonian. Let's see if I will try with this one. Hopefully it works. Okay, it works. Great. So what you can see is that we are exciting the whole system with this set of 3 laser pulses. And at the end of the experiment, we are left with a couple of states with high probability. So if I were to highlight one of these high probability states, what I can see is an alternating pattern that manifests itself. Highlighting the other highly likely state illustrates the opposite. And I have a little bit of leftover for one of these extra states. But we are focusing on the 2 most likely states, which in a sense select in an alternating fashion every other quantum bit or every other spin in the experiment. So it really corresponds to what physicians refers to an antiferromagnetic state. So having positioned spins in this section, one of their natural states in which they set up is to have this alternating up-down scenario, which can be simulated by a very easy Ising type Hamiltonian, which has been defined here. This has a different interpretation as well that we will discuss during the next session on Friday. For now, what I wanted to go through with you is to try to reproduce this experiment. So we will move on to a couple of interactive exercises. If I go back to the presentation itself, starting off with the main layout, so with the antiferromantic state experiment, which has 6 atoms in it. One of the questions I want you to look into very, very briefly is how the system evolves if we were to remove one of the atoms. So if you load the antiferromantic state experiment as is, and remove one of the atoms, the question I'm interested in is how the system will evolve. So for instance, if I were to remove this initial atom, I can just simply remove it from the experiment and run it again. What I can see is that, of course, the algorithm is still executing, so the script is still working. However, the solution has drastically changed from what we had previously. Since I eliminated one of the corners, what I can see here is that only the other alternative pattern is what survived with a very, very high probability, actually. So this is in line with what we would expect when perturbing the system. So alternatively, it's interesting to consider what happens if I were to remove one of the atoms in between, and we have already been spoiled because it's an automatic emulation, but we can look at the same experiment from this perspective as well. And what we can see is that we have different quantum state that survives, which is again the corresponding alternating state that has not been as no atoms removed from the corresponding solution. So this sort of illustrates that for these type of patterns, this laser pulse sequence is able to properly encode the Ising-Hamiltonian in a sense in order to find what we are looking for in terms of solutions for this type of problem. However, this is not necessarily the case. So what I've prepared for the last part of the session is a series of exercises that we are going to go through in order to see just how well you can already design a robust, so a generic formulation for the code. But before moving to that and giving you all the details, you need to reproduce a similar experiment. I wanted to showcase something else. So this is one of the other experiments you can load up by default. So if you click on the new one, you can see that there is a third example featuring the controlled Z gate. So a quantum logic gate as part of the features. As I mentioned, this is something that can only be executed on emulators. This is there to illustrate that neutral atoms platforms and the Pulsar software stack is able to encode and work with quantum logic gates. You can establish quantum logic gate-based systems, albeit since you are interacting on a very, very low level, so lower than what you might be used to, it can be quite a hassle to build proper quantum circuits. Nevertheless, I can showcase how the quantum logic gate would work. So on a control Z gate, I will invite you to follow up on how the information itself evolves. So as you can see, the pulse layout is sequential. So I have local low energy interactions targeting individual qubits. So for I'm working on the local channel. I'm targeting the target named qubit with this specific laser impulse. Then I will be targeting the control qubit. Then I will move to a high energy Rydberg channel locally to instill interaction between the atoms. That's how we will actually create the control part of the control gate. Each of these local Raman channel interactions correspond to a 1 qubit logic gate represented by a laser pulse. So they have specific shapes. What you are working with is actually the face to define for this shape, which is essentially a rotation gate. So as you could see, moving from the ground state 0, 0 by applying rotation gate on the first qubit by 90 degrees, I introduced an entangled state on the first qubit. Then I will rotate the second state as well to create a four-ways entanglement. So far, everything happened locally on an individual qubit. Then I'm preparing the entanglement. So I'm exciting with Rydberg, so hyper-excited states, each of the atoms to create the actual entanglement. And then I'm rotating back the control qubit just to illustrate that indeed I have entered an entangled state. So at the end of it, I have created fully entangled state between the 0, 0 and 1, 1 states, which cannot be produced by using only single qubit logic gates. So this is one of the first examples that people typically see when they start working with quantum circuits as a quantum state that's non-decomposable. That's a fully entangled 2-qubit state that for which you need a 2-qubit logic gate for implementation. You can take this further if you want to explore and experiment a bit various different setups. So as an example, I've also prepared how you would go around creating a 3-qubit logic gate. So a control CCZ gate, which again starts in a similar fashion. That you are applying a rotation for each of the atoms, each of the quantum bits. Then you create the entangled state. In this case, you are creating the entanglement with both control qubits. And then at the end of it, you are rotating it back to illustrate and highlight that the control has indeed happened. So what you can see is I have with 50% probability if the target qubit is measuring 0, then everything is 0. However, if the target qubit is measuring 1, I have an equal probability of finding the other 4 potential states on the 2 control qubit systems, which corresponds to what you would expect for a 3-qubit state. Does it have to be triangular? Not necessarily. This is the most optimal layout for this, but you can create other configurations as well. This was just to illustrate that you can really play around in a very, very low level with logic gates as well in a Pulsar environment or even with Pulsar Studio. For more information, I should have mentioned that earlier, the documentation for Pulsar is directly accessible through Pulsar Studio. So on the left-hand side, you have a specific icon for the documentation, which brings you to the online available documentation of Pulsar that contains a set of tutorials for the programming language. Some of this tutorial material is directly accessible through Pulsar Studio. So if you're interested in learning more about what the antiferromagnetic state experiment is about, there is a specific section on it. If you're interested in learning more about how the control Z gate or other logic gates are built using Pulsar, there are specific sections on that as well, just for your information. So now back to the exercises at hand. So if I go back to my presentation, I have 2 parts of this first exercise for everyone to get a bit more familiar with the Pulsar Studio system. You can start off with a new register to define a rectangular layer, or you can start off with the antiferromagnetic state experiment as well. And the first part of the exercise would be to create a register, a rectangular register with atoms in these specific positions. Again, so we are working with a 3x2 or 2x3 grid with quite round numbers for coordinates. So I've indicated the rectangle has 8 and 16 micrometers, and the Q0, so the first atom, is starting from the origin, so from the 0, 0 coordinate. So this will be the first part of the exercise to create this layer. You have multiple ways to go about it. You can try to measure it with your eye, but as I mentioned, for individual qubits, you can also work with the coordinates to have them defined in the specific positions you would want to have them. So let me quickly adjust it in my setup as well. Again, for this exercise, it doesn't need to be decimal, really precise. You can really eyeball it if you want. The idea is to create a layout of a quantum register that's quite stretched out. So this 8 micrometer distance is more of a long-range interaction. As you can see, the edge connecting them is quite thin compared to what we've seen previously. So if the layout itself is set up for this rectangular base, then the second part of it would be to define this specific pulse, this specific laser pulse that will be a simplified version of what you have in the antiferromagnetic state experiment. So I will go back to the program and illustrate what are the different values I'm looking for. Working on the Rydberg global channel, Blackman type, so a Gaussian type amplitude for the laser pulse with, as you can see, there is a physical reason for this, but one of the 3 parameters needs to be blocked because it's dependent on the other 2. So it's not free for all. There is a mathematical correlation between the duration, the maximum amplitude, and the surface of it, which is, of course, the integral. So you can only change 2 of them. So I invite you to set to something of similar values. So here I have set the maximal value for the amplitude as 3.5 with a pi radian per microsecond and an area of 1.7 pi. But it can be something similar. Again, the values themselves are not super important. It's really just to give you an idea of how you would go about. And then for the detuning, as I have seen, I've set a ramp type interaction with starting value from -12 and the stopping value of 9 and the duration that cuts off at 900 nanoseconds. So what's happening is that we are providing an increasing amount of energy, so a source term up until a limit, and then decreasing amount of it. In the same time, we are extracting information with the sink term with negative coefficient, and then switching to positive coefficient, and then abruptly cutting it off at a specific position. The reason for this is not necessarily obvious, but once you are done with the experiment, you can execute it to see what are the actual results. And as you can see that for this layout, I have 2 quantum states with rather high probability, so 30–35%. Again, the alternating pattern and the other alternating pattern, which is the Ising-Hamiltonian solution. Even though we are not using the same laser pulses before, what we have done is we have essentially reproduced a similar behavior than what we have observed in the antiferromagnetic state experiment. How to define these parameters? Typically, that's part of the algorithmic development, and that's why experimentation is key to come up with the right amplitude, the right detuning, the right shape. Is really a lot of trial and error. Understanding better the dynamics can help, but in most cases, what you are doing is you are approximating your operator, your Hamiltonian, with something that's easily implementable. or that's something that's mathematically coherent. So some of the parameters can arrive when you write out the mathematical formulation of the problem you are trying to implement, while others are results of what we call shape optimization. So tweaking around these parameters is part of the algorithmic development, and that's where Pulsar Studio can become quite interesting because you can really just play around with the parameters and have direct visual feedback on how the result has evolved. One particularity I wanted to mention for this detuning is that I defined a specific cutoff. This seems like an arbitrary choice. In order to see what happens if I were to, for instance, change it, I would extend nope, not that much, the detuning almost all the way to the end, for instance. And let's see what happens with the quantum state in this side. So once again, I'm launching the experiment, and I see something similar that is starting to converge to the same rate, but the results are much more noisy. So indeed, by having the detuning not being cut off at the proper location, the quality of the results have deteriorated quite significantly. More than that, I have a lot of the partial solutions, so selections of only two atoms, two spins for the system highlighted. So cutting off early the detuning can, in a lot of cases, stabilize the system itself. It can also help with guaranteeing a good precision. So this is not an arbitrary choice. This is a choice that has been made by the developer in a sense. For now, I will leave it at that for the pulse shaping part. So we are not going to be modifying the pulse more than that, because what I'm interested in highlighting is that, as I mentioned, when you're implementing, there are two main components: defining the geometry and defining the laser pulse. So naturally, a question you could ask is that, okay, I have my algorithm, I have my task that I want to perform, I need to encode it in a geometry, and then I need to define the interaction. But for a lot of the algorithms, what is actually defined is the interaction part, and the geometry itself is a lot of free parameters with which I can work in different fashions. So the geometry can not necessarily be part of the problem, or it can be an extra degree of freedom. So how can I find the right geometry? Or inversely, what happens if I change the geometry? Will my code, will my same pulse give me good results if I change the geometry? So in what follows, and what I've prepared as a follow-up exercise from this, is to keep the same laser pulse, but modify the register. So I have provided two triangular-based layouts for two different quantum registers. And what I'm interested to know is that if I were to define these atomic placements with the aforementioned single Gaussian laser pulse with a cutoff detuning, what would the results be for those experiments? Would it still be able to solve, in a sense, an Ising-type Hamiltonian, selecting alternating spins for the system, or would it give results that are, in a sense, completely incoherent? So with this, what you can do is you can really test the robustness of the algorithm and the stability of your method. So how sensitive it is to the geometry, which can be a very, very important factor. In the meantime, while you are working on that, I see that there are a couple of questions. So I will try to position it so that it's not in the way. So yes, indeed, I did notice the antiferrometric state experiment example is being cut off when it starts applying the second constant pulse. So it could be that there is a typo in how the example has been defined. So a workaround for it is to just simply delete the laser pulse definition and redefine it with the same parameters. And it should work just fine. I will raise it with the development team that one of the examples has some issues. I did notice the same thing, so it is not normal. But if you create the same laser pulse by hand, there should be no problem with executing it. As you have seen, it was working fine for my own example. So can you change the location of atoms, I imagine, while the pulse is acting? I admit I don't think I ever actually tried doing that with the software. It should not allow for you to change, and I think I know what's going to happen, but we can do some live stress testing of the system. That's always exciting. So if I launch my experiment and I'm moving around the atom, the answer is yes, it's able to account for it. However, I haven't released the atom, so it has not actually taken it into consideration. So visually, it is able to move it around, but if I were to move the atom around and push it, it would stop the experiment at that point in order to recalibrate, and then you could continue the experiment, move the atom around. So this is something that the software itself allows because you are working with local emulation. So you have access to all the intermediate states. So you can technically stop at any time the program and then restart it with the new states. This is, however, not something that's supported by the hardware. It's not something that it's meant to do, to move around atoms while the computation is happening. First of all, the time scale in which the computation is happening, it is less than a microsecond. Moving around the atoms is typically more on the millisecond scale. So time-wise, you would not be able to move it. Second of all, during the interaction phase, you are not allowed to interact with the atomic placement in order to avoid interference between the two different laser lights that would be acting at the system at the same time. So while the software itself allows, due to the fact that you are working with an emulator, even though it stops the experiment, so it's not a dynamically shifting continuous experiment in that sense. This is not something that the physical system would support. So apart from it being curious, this is really not something that the system is meant to do. So algorithmically, you should not rely on these kind of dynamic placements. So the atomic placement should be fixed at the beginning of the experiment to provide for realistic results. Yes, more questions. So it's able to work with multiple states. So the ground refers to in the actual states, you have access to the full state, which is able to work with 3 different reference states. So as I mentioned, we use the local channel with the Raman channel for quantum logic gates interactions, which is a hyperfine excitation level. So one of the reference states is a hyperfine state, and we use the entangled state as a hyperexcited Rydberg reference state. So technically, the system, from a programming perspective, supports having ground state, Rydberg hyperexcited state, and hyperfine state at the same time. So it is correct. And so is there detuning there to compensate the phase offset of the Rydberg state? Yes and no. So it can be viewed as such, but it really depends on the experiment you have designed. So I hope you had some time if you were working around in defining some of the layouts. I'm going to showcase some of the results for this experiment. So first, let's start with the triangular version. For which, as you can see, I'm using still similar experiment. Here I have left the detuning cutoff point at a later stage, so I can shift it back to the old one and relaunch the experiment. See what happens. What happens is that it actually manages to select the three outer nodes with a very, very high probability. So this can also be viewed as a reduced version of the alternating state. So is it coherent with what we expect? In a sense, yes. However, is it in line with what we wanted to do, which is something that we will see on Friday when we talk about this experiment from a more operations research point of view. Similarly, let's see what happens with the 7-node experiment. So as you can see, now the button has slightly changed because I have more than 6 atoms, so it's not able to immediately spontaneously calculate it. I need to click on the emulation button for it to run the pre-computations, and now I can execute the experiment just as it is, and I can stop it whenever I want. So it has pre-calculated all the intermediate quantum states you would need to have access to. What you can see for this more complicated layout is that you have a selection of quantum states, and you can go through them one by one. There are 8 more likely scenarios in total, and all of them correspond to selecting one of the 2 nodes from this block, which in a sense corresponds to some kind of alternating selection to some extent. But we are really pushing the type of geometry we have for this these state experiments to the limit. And to illustrate how much we are pushing it, I prepared a final exercise to investigate the geometry, which asks for you to define this 5-node experiment, this triangular layout, which has shifted from being a rectangular experiment to really a triangle-based experiment. We are still keeping the 8 micrometer distance, but instead of having square lattice, we have a triangular-based lattice. And I've kept the number of nodes to 5 to keep it simple, but you can add more nodes, more atoms in a similar configuration to test it. And for this experiment, currently I moved around one of the atoms. What we can see and what we can notice is that as a final state, there is still quite likely, and the most likely, not by much, but the most likely selection is, in a sense, trying to select an alternating solution. However, with more than 20% probability, we have 2 alternative states, which has allocated the same spin, the same orientation to neighboring nodes, neighboring atoms. So this illustrates the fact that the algorithm was working very, very well for specific geometries, for specific layouts. But once we have really moved away from the rectangular-based or geometrically similar architecture and moved to a triangle-based system, here completely the same sequence, this sequence is no longer functioning as intended. So mathematically speaking, it's coherent with what we would expect, that the geometric layout has an important impact on how your algorithm is performing. That's why to develop on a neutral atom system, it's not enough to define the interaction Hamiltonian, so the energy you send to the system. It's also very important to define a proper geometric layout, to have the atoms in specific positions. And to test your algorithm, you need to keep in mind that you need to keep the geometry, the topology of the geometry within the same category, because the further away you move from the initial geometry, the less likely your solution would be working. So this will have a lot of impact when we will start designing applications and actual use cases. And we will see a couple of examples on Friday and as well as next week for the operations research side. And with that, I've reached the end of what I wanted to share with you for today. I don't see any more questions for now, but we still have 10 minutes or so. So if you want to ask anything else, feel free. I hope you managed to connect to the tool and get some inspiration to get started with working with neutral atoms type systems. So as you can see, Pulsar Studio is relatively easy to manipulate. So it's really an interactive graphics user interface. Knowing what to manipulate is the tricky part. It requires a bit more advanced understanding of the underlying mathematics. For now, I didn't go into too much detail because that was not the objective for today, to design meaningful experiments. The objective for today was just to play around with it, to get an understanding how the geometric layout works, how the laser pulses work, what they actually represent, what they actually mean. This is something that we will take a look at on the next session on Friday, where we will discuss some graph optimization problems. So are there any other questions before we end today's session? So there is a question, can we interpret that phase is the magnet and detuning is direction? I'm not sure what you mean by magnet and direction exactly, but you mean for the Ising type Hamiltonian for the antiparamagnetic state representation? Okay, amplitude. To simplify the visualization, yes, I would say that you can look at it that way in a sense, but it is really, really simplifying the scenario. But we will definitely look into that in much more detail on the Friday session. What's the good visualization? What's the good interpretation of what amplitude is and what detuning is? For now, what I really would say is that it refers to the source and sink terms in the Hamiltonian. So it correlates to the one-body interactions, but with opposing signs. But we will discuss this further on Friday. If there are no more questions, I think we can end today's sessions here. So hope you will be able to make it for Friday sessions, where we will look at more on the application side and build up on what we have learned today. In any case, if you have more questions, feel free to reach out to Qcenter and to us as well from Pasqal. So thank you very much for your attention. And hopefully see you on Friday.